Okay, today we're going to do the law of conservation of energy. Statement of law of conservation of energy, you've probably heard it like 40 times in your life. Here we go. Energy cannot be created or destroyed in a mechanical process, only transferred. So you now know about 3 different types of energy that you can calculate. You know about kinetic energy and the 2 potentials, gravitational potential and elastic potential. So the conservation mechanical energy says that the sum of all of those energies at any one point in time, they're all equal to the same number. So we would say total mechanical energy is equal to all of the kinetic energy plus the sum of all of the potential energies at any one time. So it's the sum of all energy in a process. Okay, so over here we've got, consider a shot put ball falling into a grassy field. Okay. So at the top, at point A, you have a ball being held at some height above the ground. So is it moving at that point? No. If it's not moving, can it have kinetic energy? No. But it is off the ground, so what kind of energy do things have that are off the ground? Potential, okay? So the energy at point A is UG. So you have to define which potential. Is it gravitational or is it elastic? So in this case, it's gravitational, so you call it UG, okay? All right, and then at point B, it says the ball is halfway to the ground. So it's falling. You've dropped it now. And it's falling. It's still off the ground, but you see those little lines at the end of it? That means that it's moving. So what kind of energy does it have now? It doesn't have UE because there is no spring. What? Kinetic. Okay, so it's got kinetic. And what else? Potential, gravitational potential, because it is off the ground. Okay, and then part C, it's the moment before the ball is stopped. It has no height, okay, but it's still moving. It's like the moment that it strikes the ground, okay? So it has no height, but it is moving as fast as it can possibly go, okay? So what type of energy does it have at point C? Kinetic energy, yes. Okay, and then at position D, it says the ball has embedded itself into the ground. What kind of energy does it have now? None.
None. Oh.
It's stuck in the ground, y'all. It's none.
Well,
I know, it's a trick question.
Getting ready to, like, bounce back up.
It's not going to bounce back up. It's embedded in the ground. It's done. You have to use energy to get it out. It's stuck in the ground.
I was like, oh, it's oval shaped, yep. So it's like falling.
I know, you think that, but no, it's not. All right. So, at the front of your packet, yes, sir?
Since it can't, like, energy can't be destroyed, how is it not?
It's lost to the ground. So, energy can be in multiple forms. So you can have energy in sound, in light. Those are the main ones. Heat, yeah. So the energy in the fall is probably, I mean, have you ever heard something when it falls? It like... Okay, so it does convert energy to another form of energy. So it's still transferred in the process. Yes, sir?
What does the, at the top, the conservation of mechanical, what does this after the K mean? Is that?
Sum. That's an epsilon. It means the sum of all potential. The sum of all potential. Okay, at the front of the packet, you've got a little, on the assignment sheet, you've got a little graphic here with a little guy on a roller coaster. Let's talk about this little guy on the roller coaster, okay? So it says, you have a roller coaster. It says, as a coaster car loses height, it gains speed. And then the potential energy is transferred into kinetic energy. Okay, so losing height means it's going to speed up. And then as the coaster gains height, it loses speed. So the KE is transformed into PE. So at the top, when it's starting to go, you have very high potential energy. So high UG and very low kinetic energy. So stop moving very fast at the top of the incline, right? So low KE. And then down here at the bottom of the hill, it's moving as fast as it can possibly go, but it's on the ground. So it has very minimum or no UG, and it has the highest amount of kinetic energy that it's going to have. Okay? And over here, you have low potential energy because it is slightly off the ground, but it's still moving. So what's the difference here? If these both have, this has UG and KE, right? So let's say up here, let's say it's at the moment the roller coaster like lets go. So it's not moving, but it's sitting on the incline. So if it's not moving, what is the total amount of energy up here? The total amount of mechanical energy, what is it equal to? Which one of these? UG or KE? UG. So down here, where it has no height at all, okay? Bless you. It has no height, but it's moving. What do you have mechanical energy-wise? Kinetic. You only have kinetic.
So is mechanical energy the bigger number?
It's all of the energy.
Oh.
And then over here, it is off the ground, because look, here's the ground. So it is off the ground some distance, and it's still moving. So over here, your mechanical energy is equal to potential and kinetic. It's both. But guess what? This amount of energy, the mechanical energy right here, we'll call this mechanical energy 1, we'll call this one 2, we'll call this one 3. Mechanical, that's not an, it's an M. Mechanical energy 1 is equal to mechanical energy 2, and that's also equal to mechanical energy 3. So if you know just a little bit of information, bless you, you can kind of fill in the blanks and find H or velocity or something at different parts of the roller coaster ride. Okay, because mechanical energy will be completely conserved in this physical process. There's no embedding the roller coaster with the people in it in the ground like there was that ball, okay? Okay, so this is a pinball machine. This is also in your packet. So you have a little pinball machine, and here you have a mass that is compressed to spring 2 meters, and then there's the spring constant, 75 newtons per meter, okay? And then after the pinball machine like lets the spring go, it's going to push this little mass, and here it's still, it has no height, but now it's moving at 10 meters per second. Then it goes up an incline, okay, and now it's moving a little slower as it goes up the incline, and now it has some height. And then up here at a height of 5 meters, it doesn't appear to still be moving, okay? We're going to calculate that and verify that in a minute. But, okay, so it says for a 3 kilogram object against a compressed spring, when released, the object moves up the ramp until it stops. It does tell us it stops. Assume there's no friction on the surface. And for gravity, go ahead and just round, they're saying just round it to 10 meters per second squared. Just to, you can do the math in your head, basically, is what they're trying to make you do. All right, so then it says, what kind of energy does the object have at position 1? So at position 1, it's not moving, and there's a spring. So what kind does it have?
None.
Yes, it does.
Oh, I mean,
Which kind of potential? Elastics. This is UE. So it has UE right there. Now at position 2, what kind does it have? Kinetic. It's moving, so it has kinetic energy. At position 3, it's moving and it's off the ground, but it's not touching a spring, so what is it? Kinetic energy and UG, yes. And then at position 4, assuming it stops, what type does it have?
UG.
Potential, UG, yes. It doesn't have any KE because it's stopped. It's not moving at that point. It tells us in the problem. So, label it with the type of energy or energies at each position. Okay, so the first one we have UE. Second one we have KE. Third one we have KE plus UG. And then the last one we just have UG. It says calculate the energy at position 1. Okay, so then UE equals kx squared over 2, right? So they tell us K is 75. So 75 times x squared, so that's 2 squared over 2. Okay, so that's basically 75 times 2, which is 150 joules. Okay, how did I do that in my head? You have 2 on the bottom, you have 2 squared on top, so I can cancel the 2 and this square, and so it ends up being 75.2, so that's 150. You can do math in your head if you want to. All right, so then part D says to calculate the energy at position 2. All right, so position 2, we only have KE. Okay, so KE is mv squared over 2. So the mass is 3. The velocity is 10 squared over 2. Okay, so 10 squared is 100. 100 times 3 is 300. 300 divided by 2 is 150. So that's 150 joules. Okay, so far, the law of conservation of energy is holding true for all of our math so far. Okay, and then part E says calculate the total energy at position 3. Okay, so position 3, so we have it's moving and it has gravitational. So that's UG plus KE. So that's mgh plus mv squared over 2. Okay, so we're going to plug that in. So then 3 times 10 times the height is 1.8 plus 3 times 8 squared over 2. And I'm not going to do that in my head because I'm not going to waste my time. So 3 times 10 times 1.8 plus 3 times 8 squared over 2. 150. Hey! Kind of predictable now, isn't it? Joules. All right. And then calculate the energy at position 4. So we're assuming if it's stopped, it only has UG. Okay? So UG equals mgh, which equals 3 times g, in this case is 10, times h is 5. Okay? So 3 times 5 is 15. 15 times 10 is 150. All right, so we're going to do number 3 at the bottom of the page. It says a 5 kilogram object compresses a spring 0.25 meters, and we want to calculate the energy it has when the spring is compressed, first of all. All right, so when the spring is compressed, so before, let's label our picture. So before, what kind of energy is in here? UE. So before, we only have UE. Afterwards, okay, what's going to happen? It's going to push off and it's going to go, and we're going to assume that this is a frictionless surface. So then afterwards, it's not touching the spring anymore, but it is moving. So what do we have? KE. There's no UG because it's not going to come off the ground, okay? So it says calculate the energy it has when the spring is compressed, all right? So UE equals kx squared over 2. That's the formula. So then we're going to plug that in. They give us our K is 60. They tell us our x in meters is 0.25 meters squared over 2. Okay, so that's 1.875 joules. Okay, so we've answered part A. Then we've actually already answered part B. What kind of energy does it have when it's released? That's the after, that's KE. If there was no friction on the surface, how much energy does the mass have after it's released? So if there's no friction, there's no energy loss to thermal or sound or light or anything else. It's not going to make sparks on the surface. So it's not going to make a sound. Nothing will happen except it will move. So then what must the energy be after? The same. It's also going to be 1.875 joules. So that means that's your KE after. So it says then, calculate the velocity of the object afterwards. So if we know our KE and we know our mass, KE equals mv squared over 2. So you can just plug it in right there and find v, or you can rearrange the formula first and solve for v. Which one do you prefer? Plug and chug or rearrange first? Plug and chug, you got it. So 1.875 equals, our m is 5, so that would be 5 times v, we don't know v, squared over 2. Okay, so 5 over 2 is 2.5, so 2.5 v squared equals 1.875. So then I just divide by 2.5 and then take the square root of that to get v all by itself. So 0.87 meters per second because it's velocity.